We continue with the morning session, the second talk by Carlos Gabriel. Gabriel? Gabriel?
Yeah, that's fine.
With the title, Double Homology and Sphere Triangulations.
Well, hello, everyone. And well, first of all, thanks to the organizers for letting me speak here. Right, so what I'm going to talk about today is about two manuscripts that I have. The first one is joined with Donald Stanley, and yeah, that's about it. So first, just going to set up some notation. So when I talk about simplicial complex, I usually use the letter K. And it's going to be an abstract simplicial complex. Just as a quick reminder, that's just the condition. That's just a subset of the power set on M vertices, such that it contains the empty set. And for every sigma tau, with tau a subset of sigma inside of the simplicial complex, tau is in the simplicial complex. It's just closed under inclusions. And another notation is that of full subcomplexes. So we have a subset of the interval 1M, then K sub J just denotes basically all of the simplices in the simplicial complex that are inside J. Right. So I'll just start with a bit of motivation for the definition of double homology. And just to state the structure of the talk, the first half is going to be me talking about double homology in general. The second part is about some results regarding sphere triangulations. So the origins of double homology can be traced back to TDA, to topological data analysis. The usual pipeline when you want to do topological data analysis, you start with some data set. And from that, you build some metric space. And using this, you can build a filtered simplicial complex. This is usually a check complex or a Vietoris-Rives complex. Not going to go into the details of what those are. And after you do this, you can take the persistent homology of that. And by studying this gadget, you can obtain a lot of information about the data set. But the thing is, that information in some sense is kind of global. And one really nice idea to study those data sets in a more local sense is to, instead of looking at the whole set of vertices, you look at subsets of it. So with that in mind, one idea that popped out a couple of years ago was to add a middle step here. So when you have filter simplicial complex, that thing induces filtered moment angle complexes. And then after you take this moment angle complex, you can take the persistent homology of that, and that gives you strictly more information than just looking at the filter simplicial complex. The thing is, this approach has three major drawbacks. The first one is that, the persistent homology of moment angle complex is really big. Really big as in the graded rings have incredibly large ranks, so it's really it's not that manageable. The second drawback is Well, computing this is of exponential complexity. So it's really it's really slow to actually do data analysis on that. And the third thing is the persistent homology of set K is not stable. Right. By stable, I mean that if you modify the data set a little bit, then the pH of set K will most likely be widely different. And the approach to solve those three problems was proposed by Limonchenko, Taraspanov, John Song, and Donald Stanley. And it's precisely this construction of double homology. So how do we do it? So just a reminder. We have explicit formulas for the homology of the moment angle complex. One of them is just by looking at the Stanley Rising ring. And the other one is as a total algebra, and by the Hoxer formula, this is precisely the same as the direct sum or all subsets of M of H star of Kj. Well, reduce HK J. Where I guess I should mention here that this guy is inside of set. I'm going to use this notation U1 up to UM. And the degrees of these BIs and UIs are, but they're actually by degrees. I think this one is 0, 2. This one is -1, 2. And the differential maps, it was UI to BI and BI is 0. And about the degrees of the other one, we have the H. Well, if you notice that all the degrees are negative, comma, even. So then we just do -k, comma 2L of set K. That is the direct sum. J as subset of M, where we filter through the sizes of L. K sub J. And this is of degree, I think it's L minus K minus 1. No, it's upper. L minus K minus 1. Right. And we have a similar decomposition for homology. You can look at this by just looking at the BBCG decomposition, and you'll see it immediately. That is exactly the same thing, just in homology. L minus K minus 1, K sub J, where J is a subset of M, and the size of J is L. So then how do we define this double homology? The idea is that we can, instead of looking at all of the homology of the subcomplexes, you look at how does increasing the size of increasing or decreasing the size of this subset affects the whole thing. So you can put a differential on this homology and call it CH. Let's see, yeah, CH. I'm gonna do homology instead of cohomology from this point on, actually. It's just gonna be H of set K. And the differential that we will define will map from H sub minus K to L set K into H minus K minus 1 comma 2L plus 2 of set K. And this is going to be some sign times the sum of overall subsets of M of size L of, again, some other sign times the map induced by the inclusion of the symmetrical complexes X not in J of A sub J included into X. This is L minus K minus 1. Right. These signs basically just tells the position of X in the J, and this sign is L minus K minus 1. It's so that this together with the differential of the moment angle complex forms a bicomplex. And most of the time I'll just ignore this sign. Right. And the homology of that is, well, the homology of that is just going to be the double homology. And I'll just denote it by HH minus K 1 to L. Right. I guess something to notice is that the differential doesn't change this. Well, that's kind of obvious from the definition. But then when you try to compute this, it becomes a bit cumbersome to deal with these indices. So instead, I started using another by degrees. Instead of 2 under, you can put 1 under, 1 upper. And this is just going to denote H. Actually, let's do, let's see. This is just going to denote CH of, what was it? It was J minus L, comma to L, set K. Okay. Why is this more convenient? This is more convenient because when you look at the Hoxha decomposition, this is just going to look as H under J minus 1 set K. And the size of J is just going to be L. Right. You can use whichever gradient you want. Most of the time I prefer to use that one, but another times it can be useful to use the other one. Right. Okay, so I guess I should explicitly say it. This J will basically represent the homological degree of this guy, and this represents the size of the thing. So then when you apply the differential, the only thing that changes is the upper one, not the lower one. So actually, instead of having just one chain complex, you have a bunch of parallel chain complex when you look at the lattice. Right.
So, sorry, I have one question.
Yes.
What does the CH stand for? The CH.
It's just like it's just the notation for the cochain complex that you get from this with this differential. It's just to differentiate between the homology and the cochain.
Okay.
Yeah.
Your expression for the differential doesn't actually say what the differential is.
No. I'm just saying this is some. I guess this is the only thing that is missing. Explicitly, this is, you can write this as, I think it's epsilon JX, where epsilon JX that is -1 to the number of things in J that are less than X. It's just the position of X in J. I'll just do a quick example of this, probably trivial examples. You can look at the 4 cycle. Right. The CH is going to look something like this. It's going to be the reduced homology of the empty set. I'm going to increase the size of the subsets in this direction. Then that goes into 0. Then that goes into the things with 2 elements. So that's 2, 3, and 1, 4. That's the only non-trivial ones. So that's H0 of K 1, 4, and H0 of K 2, 3. That goes to 0. And that's how this CH looks like for that one. And if you notice, well, all of the differentials are trivial, so then the homology is just going to, sorry? All right, you're right. Then the H1 of the whole thing. Thank you. If you notice, the differentials are trivial, so then it's just going to coincide with the regular homology. And in degrees, this is just going to be HH is set in degrees 0, 0, 1, 2, and no, it's 0, 0, 2, 4, and it's going to be set squared in 1, 2, 0 else. All right. Another way of noticing this is that this guy is the suspension of the 2 points, and it's a kind of trivial computation that the 2 points have double homology of rank 2. And why is that important? That is important because one of the key properties of HH is something that is inherited from the moment angle complex. That is that the HH of the join of 2 simplicial complexes is just going to be the tensor product of the both HHs. Right. Okay, so that's one of the properties that I want to mention. The next one is, right. I guess something that I didn't clarify here is that I'm allowing those vertices. That is that there can be a vertex that is in the vertex set, but not in the simplicial complex. And it turns out that the degree 0, 0 set K is going to be 0 if and only if, actually, yeah, it's going to be a set if K has no ghost vertices. And 0 else. So in some sense, this degree detects the ghost vertex of the thing. Another property that is kind of important to this kind of constructions is the functoriality. That is that when you have, it's not functoriality in the usual sense, it's just that when you have an inclusion of 2 simplicial complexes, both on M vertices, then the inclusion induces a map in HH that goes, well, it's not a question. It goes like a set L. And there's a map in the other direction. Turns out that if you have a full subcomplex, then there's another map that looks like this to HH. So, personally, I call this one phi and this one psi. But I mean, we use those letters for everything, so it doesn't really mean much. Right. Okay. Let's do one more example before the next property. Instead of just this, let's just look at the, again, the fourth cycle, but now there's a chord between two vertices. Now the CH will look like H minus 1 of the empty set goes into 0. That goes into now H as 0 of K14. And that will go into two guys, H1 of K123 and H1 of K234. And both of these will go into H1 of the whole thing. Now again, these two differentials, these differentials are trivial. So then these guys persevere to the homology. But this one is not. Just if you look at the thing, this one is generated by this cycle, and this one is generated by this cycle. And this one just has those things. You can write it as those two things. So in this map is actually just going to be the identity module of some signs. So it's an isomorphism, and this canceling the homology. So then HH of this guy is just going to be a set in degrees 1, 2, and in degrees 0, 0. So why do I mention this example? Well, it turns out that, well, one of the first computations that were done about this is that most of the time you get this, that the double homology has this form. What I mean by this, I mean that there's a class of simplicial complexes that there's a very large class of simplicial complexes that has whose double homology has exactly this. This is shown by in LPSS. That is that when K is another simplicial complex related to some simplex through a proper phase, then HH of set K is concentrated in degrees 0, 0, and 1, 2. Okay. Now this doesn't have that form. Sorry, this doesn't have this form. This is not the union of a complex and a simplex, but it also has this strange shape. So however, you can modify this a little bit. So instead of gluing one simplex to a simplicial complex, you can glue two simplicial complexes through a proper phase. And that is what we call being wedge decomposable. That is that K is like K1, disjoint union through a phase of K2. And it turns out that any wedge decomposable simplicial complex has double homology. So this is a result from me and Don Stanley. And the proof is kind of straightforward, I guess. The idea is that if you have your complex that where this guy over here is a simplex, you can include this into the same one, but you feel one of the two. And if you look at the CH of, sorry, if you look at the CH of this, you can fit this in a short exact sequence that looks like I guess set K1. And from the second property, this is acyclic. So then this guy over here is a quasi-isomorphism. Okay, so that's the first result that we got about that. Let me see what else we have. Right. Are there any questions so far before I move on to the next thing? Yeah.
It's an invariant of K, but can you say anything if ZK1 is homeomorphic to ZK2?
I don't think they have to be homeomorphic, yeah. That's a good question. But I don't think that they have to be. Yeah. Right. So at this point, I'm just listing properties of that thing, so I might as well just go on with in that direction. So this degree 1, 2 seems to be very special, and it turns out that it is. And what it's measured, just as the 0, 0 is detecting the ghost vertices, what the 1, 2 is detecting is actually that the simplicial complex is not neighborly. So what do I mean by neighborly? It's just that it has as many p simplices as the full simplex has. So that just means that case of J is delta p for every J of size p plus 1. And one of the other results that we have is K is p neighborly. If and only if K is p minus 1 neighborly. And H in degrees p plus 1 is 0. I think this is very direct when you just look at the ordinary homology of set K, but it's not as clear when it's HH. Right. And the last property that I wanted to mention is is one that is also inherited from the topology of set K. That is that, well, in ordinary homology, we have that H set K is a Poincare algebra. If and only if K is Gorenstein star. For those who don't know, that's basically just says that it's a homology sphere. And we don't have that equivalence in double homology, but we have at least this implication that HH is still. Okay. So then, well, I don't know. I just found that this was pretty interesting because I'm personally interested in triangulated spheres. So at that point, I just started wondering how much can you relate the combinatorial properties of the spheres with the properties of HH? And it turns out that you can relate it quite a lot. Let's see. Right. So just this Poincare algebra duality. I'll just explicitly state the degrees for the duality. That is that HH of J L is going to be isomorphic to HH n plus 1 minus J n minus L. It's okay. The first computational result of this was also done by, oh, yeah, n is the dimension of K as a sphere. The first result that came out of this was in by Limonchenko, Panov, Song and Stanley. That is that if you look at dimension 1, you can explicitly compute the double homology of that. So use that the double homology of an M cycle. This is just going to be setting degrees 0, 0, 1, 2, 1, comma, m minus 2, and 2, comma m. Right, so it's the two that appear from Nogos vertices and neighborliness, and their duals and zeros. So that's done for all one spheres. The natural direction to go here is to look at two spheres. But it turns out that two spheres are not as simple as one spheres. For starters, the argument that they use here is that you can take a cycle and then include it to the same cycle, but you put a chord in here, just like we have in those two examples. And in most degrees, this is going to be a quasi-isomorphism. And in this degree, this is going to collapse because of, sorry, this is going to induce a quasi-isomorphism with the kernel of this map. And you can compute the homology of this using a spectral sequence argument. But we cannot really do this with two spheres necessarily. And that is because all one spheres are what we call non-primitive. And that just means that you cannot write it as, sorry, they're not primitive. So that means that you can write them as the connected sum of two other one spheres. So in this case, this is going to be like m minus I and I plus 2. Right. So what happens if we have a non-primitive sphere triangulation? It turns out that we have exactly the same thing as before. So if K is a non-primitive, n sphere on M. Then HH is going to be, again, exactly the same thing. It's just 0, 0. One, two. And their duals being n comma n minus 2 and n plus 1. And the argument is basically an analog of that. But instead of filling one chord, you're filling the simplex through which you're taking the connected sum of these two guys. Right. Yes, I guess. No, I don't think so. You don't want it to be the boundary of a simplex, but that's primitive. Yeah. So that's the result of primitive triangulations. Sorry, non-primitive triangulations. So what about primitive ones? Those are usually the more interesting one when you want to study the triangulations. And the answer is we don't really know. So some quick examples. When you got the boundary of a simplex, HH is of rank 2. That's a very straightforward computation. When you got this non-primitiveness, that thing is going to be rank 4. But when you allow the spheres to be primitive, it seems like it can be any rank. We don't really know that for sure. As some quick examples, you can take CM join S0, where M is greater than 4. And this thing is going to be of rank 8, just by looking at that previous result about M cycles. And I wrote down a program that computes HH, and we have constructed spheres such that ranks are all multiples of 4 up to 32. I haven't really found any higher rank spheres, but I'm pretty sure they're out there. So a question here is, can primitive spheres have arbitrary, by arbitrary meaning mult of 4 and greater than 8 HH rank. My intuition tells me that yeah, that's surely possible. That is because it was recently shown that you can a way to construct complexes of any HH rank. So in principle, you can construct any complex of any given R halves, and then turn that into a sphere and double the rank by duality. That's in no way formal. That's just my intuition. That's what my intuition says. And I really want this to be true, because that also gives another way of constructing triangulations with arbitrary HH rank, because of my second result on this. One natural way to study triangulations is to see what operations do to them. And probably one of the most controllable operations that you can do on a sphere is removing maximal simplices. So then How much time do I have? Okay. I'm just gonna, I'm basically just gonna state this and that's gonna be it. If K is a triangulated n-sphere, then an L sub sigma is just gonna be K without sigma for sigma maximal simplex. Then we have two cases. If K is one neighborly, then HH, well, the rank of HH of set L sigma is just gonna be the same as the rank of HH sets of K. It's not that the homologies are the same. Actually, what happens is that the top class that appears in this one goes to a one-dimension lower class. And if K is non-neighborly, then the rank is going to be reduced by 2. Here, what happens is that the top class and the second to top class disappear. So yeah, that's more or less the reason why I wanted this to be true so bad. Because, well, if you have multiple of 4, you just reduce to get any rank that you want. Do we have anything else to say? Yeah, I should probably stop now. I think that's all I wanted to say.